Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Julian Carlin with us today. Hello, Julian.
Hello, good morning or good afternoon, wherever you are.
Yeah, so let's see. We are shooting this on June 15th, Thursday at about 4 p.m. And I believe it is 9 a.m. in the morning over in Australia.
Yep, that's correct.
Very cool. And what part of Australia are you in, Julian?
I'm currently in Melbourne, in
Melbourne.
Victoria, so
Okay.
south corner.
Let's see, and it is winter there.
Yes.
Does it snow in Melbourne? That's a nice
No,
question,
no.
but I
I
don't
mean,
know.
next week it'll be around sort of 12 degrees Celsius. So
Okay.
it's cool, but it's not like freezing.
Okay. Very
I
cool.
actually went on a nice little, 1 week holiday up to our tropics in the Queensland. So
Mhm.
I'm feeling some, lingering warmth from that.
Very cool. Very cool. And what's your position there in Melbourne?
So I'm at the end of my PhD. So I submitted my PhD a month ago, and so I'm waiting for the examiners to get back. Thank you, with any revisions needed, and hopefully that'll be fine. So I've started a little postdoctoral, 1 year position with my supervisor.
Right. Well, great. So I get to call you Dr. Carlin. So
Oh,
that's
that'd be cheating.
Dr. Carlin. Most excellent. Very cool. And I admire your shirt there. I like that shirt with
Thank
the
you.
stars on it. Sort of matches a little bit what I got going here.
Yeah.
Very and Julian, what do you like to do for research?
So I've actually had a fairly varied career so far in academia. So my PhD consisted of many different sorts of projects. So I really started in pulsar glitches. So a very different area to what we're going to be talking about today. Well, somewhat different.
It's a time series. It's a time series.
Yeah, there's events that happen in time,
Yeah.
which I guess is most of physics. Um, so I started thinking about statistics of pulsar glitches and how we can think about them and model them as a sort of big system that has stress and releases some of that stress over time.
Cool.
I did a bunch of projects there, and then I took a little break and did an easy, not very easy data analysis project, searching for continuous gravitational waves,
Oh, yes, yes. Very nice.
LIGO data.
Right.
So this was using O3 LIGO data and searching for continuous waves from a specific type of binary target.
Yep.
Which doesn't have much to do with pulsars, besides the fact that there's neutron stars in the sort of heart of them. But the varied interests. And then in the last year of my PhD, I switched gears a little bit to solar flares. This was always sort of an idea that maybe the things we've been doing in pulsar glitches could be applied in solar flares.
Yeah.
My supervisor Andrew Malados has a good relationship with Mike Wheatland, who he actually did his PhD with back in UCID. And so they had sort of been talking about this idea back and forth, and Mike had inspired Andrew sort of a decade ago to think about this in pulsar glitches, and now Andrew's come back to him with, okay, we've got some machinery now. Can we learn something?
Very nice. Very nice. Well, that's going to be a wide-ranging thesis.
Yes. It was a bit tricky to think of, like, okay, well, how do I
you wrap that up
frame this in a one title or even in an abstract or something? It was a little bit of a struggle, but you can make anything work.
You got there. So that's good. Cool. And that is going to bring us to this very awesome APJ article. It is open access, people. You can go get a copy for free. Go grab one. A statistical search for a uniform trigger threshold in solar flares from individual active regions. And Julian, take us away.
Okay, so this is a paper we wrote with my supervisor Andrew and Michael Wheatland. I'll be calling them Andrew and Mike from here on for shorthand.
I'm with you.
And so Andrew and I are in Melbourne, and Mike is up in Sydney. So this paper is basically our foray, Andrew and I's foray into solar flares. This is not a field that either of us had published in previously. Andrew obviously has ties to Mike back from his PhD days. And so it's sort of like by osmosis heard about solar flares and knows about the field. And obviously we have Mike for the expert sort of modern opinions. And so this was us taking an idea and a methodology that we developed to help try and understand pulsar glitches, which I'll return to in a second, and using that machinery to understand a different sort of phenomena, high energy phenomena, solar flares, which have similar-ish properties in some ways. And it's quite different in others. One of the major ways it's different is that there's actually a fair bit of data for solar flares. We've been looking at the sun for, a good 100 years, pretty continuously with pretty good telescopes, which is not the case for pulsar glitches, where we look at them sporadically with very good telescopes, but only sporadically.
Right. Volume is less.
Yes. And so part of the sort of fun with this project was that we could use this sort of methodology that we built up for pulsar glitches and be like, okay, well, now that we have like 100 times more data,
what
can we do? What different sorts of tests can we do? What sort of questions can we ask that are different? Okay, so let's go solar flares. What is this idea? What could we be applying from pulsar glitches to solar flares? So the way we sort of introduce this is that historically in the literature for solar flares, there are sort of two main camps of what causes them, what triggers them. One is that there is this sort of, well, first I'll start with this pretty major consensus that a solar flare is a magnetic reconnection event.
Okay.
So magnetic fields stressing, something happens. The flare lines reconnect, and that releases a whole bunch of energy, and perhaps that's associated with a coronal mass ejection, perhaps not, but we're not too interested in the details therein, although they are quite interesting. The idea is that energy builds up and some is released.
Got it. Yep.
Now, okay, so there's lots of good reasons to believe that if there's more energy, or energy density really, in this active region in the corona, a reconnection event is more likely.
Yes.
That makes intuitive sense. And there's also intuitive sense that over time, energy will build up. You're depositing more and more energy by photospheric, subphotospheric motion, convection, and all these sorts of things. Okay, so energy builds up over time. Eventually, it'll hit some breaking point where something has to happen. Something has to give.
Okay.
Now, this is the stress relax model, or stress accumulation relaxation.
Okay.
Rosner-Viana in 1978 sort of did the first sort of mathematical sort of construction of this sort of idea.
Okay.
And Mike and many other authors have sort of taken it on and expanded further and tested it in various ways, and sort of tried to look for various sort of signatures of this. And what was sort of often described as sort of complementary, or opposing, or perhaps the other alternative is this sand pile or avalanche model. And this is inspired by the sort of canonical numerical sand piles of Bach, BTW. So this is in paragraph 1. Bill, sorry.
I'm waiting.
The 1987 papers. These are sort of like real canonical papers that sort of go into how you can understand what's called a self-organized critical system.
Yes.
Where the system has a driver, and it's an external driver, but this driver can be stochastic or various versions of the model. But the thing is, you drive the system and it organizes itself into a state of criticality, and so it fluctuates around this sort of marginal stability.
Okay.
So it'll release some energy, and these energy releases will then distribute the energy to neighboring cells, and it'll build up more energy over time, and then these sort of releases and builds up. Was a really cool idea, and lots of people took it to be like, what physical systems is this really modeling? Because Bach et al. Were doing a quite idealized sand in a mountain.
Right.
And one of the great applications was this Lewin Hamilton idea that perhaps solar flares are like this.
Yeah.
You have these sort of convective cells that work as your sort of cells in your automata, and you're depositing energy in them, and then you release energy, and the energy gets distributed to neighboring cells, and perhaps solar flares are self-organized criticality. And so historically, these two ideas, stress relax, the Rosner-Viana, and Hamilton avalanches, were sort of different. They were considered separate and there were some statistical predictions that they would make that the others wouldn't. And so often there was this desire to sort of try and find evidence for one or the other, which makes sense. You want to try and understand what causes glitches. These sort of seem like kind of different ideas, but really, our opinion, perhaps as outsiders of the field, was that there is a continuum between them.
Yeah, maybe they're not so very different.
Yeah. As always, when you have a bimodal thing, perhaps actually there is some middle ground between those two edges.
Or perhaps.
And so one way to get to this sort of intermediate regime, or trying to understand where we are in the spectrum between these two models, is by having a sort of machinery that allows you to move between them by turning a control parameter knob between them. Okay, and so that's setting up why we might want to have some sort of better mathematical machinery.
Good, very good.
Now, I'll sort of skip over a bit more of this appendix because we come back to it later when we talk about the data. But basically, I'm sort of introducing that, yes, there's historical data sets, and people have found different statistical signatures by looking at it in different ways. I won't talk too much about the glitches at this stage. So Pulsar Glitch, I guess I probably should introduce Pulsar Glitches just so we're on the same page.
Okay.
So pulsars are neutron stars with a beam, very stable rotators, very stable in a sort of long-term sense, but we have such precise timing of them that we can see these very minute spin-up events. So once every couple of years, some pulsars do this thing where they increase their rotation frequency by a tiny amount, like 1 part in a million or smaller.
Right.
And we can measure these and determine that they're not just random noise, that there's signatures that we can see that are consistent between these events, and they're analogous to solar flares in the limited sense that we believe that there's the same thing of stress relax happening, where stress is building up inside the neutron star, and I won't get into how it does that or why, but stress is building up and relaxing when a glitch happens. And so to try and understand glitches, Andrew and a past student of his, Will Fulgenzi, in 2017, really broke some new ground by working out some of this mathematical machinery called the state-dependent Poisson process, SDP.
Cool.
And this process, what was that, sir?
State-dependent Poisson.
Yeah. And this is a kind of, I'll get to it in the next chapter, but from this machinery, you can make predictions about long-term statistical things using just waiting times between events and sizes of events. And so in Pulsar glitches, this is all we really have. We know how big a glitch is and how long between it is, but we sort of don't have any other data. We can use a little bit more, but for the time being, that's all we've used historically, is these sort of quite crude
glitch,
things. But you can still do a lot with that. Sorry, I'm just getting a phone call. I'll turn my phone off.
All good.
Okay, so the idea is that we're going to try and make the same sort of falsifiable predictions in the solar flares regime using this state-dependent Poisson process. Then look in the data, see if we see those predictions. If not, we've falsified some aspect of this machinery applying to the data.
I like that. Very good. Yes.
Okay, so let's go on to chapter 2.
Okay, I'm doing Geos. Goes. Okay. We have some state-dependent Poisson
Yeah.
processes.
So, here's the maths. There'll be a bit of maths later, but this is actually much of the extent of the maths of this paper is in this equation. So the state-dependent Poisson process does something kind of interesting by saying, okay, there's this hidden property of the system called stress.
Okay.
We can't directly see the stress of the system, but we're going to assume that the stress is a continuous function of time. Actually, technically, it's a discontinuous function, but it's a function of time. It starts at some value x0. It increases with time, and it has these jumps, these decrements, where it'll decrease by delta x amounts at certain times. And so it'll be doing this sort of like dance up and down of linearly increasing secularly between events, jumping down when an event happens, and then building back up again.
Yes.
In this equation, we have our stress and our time expressed in dimensionless units, which is kind of important to sort of recognize that we're hiding a bunch of numbers here.
Right.
So, X is expressed in a unit of critical stress. And so this critical stress is a stress which will never actually be reached in the state-dependent Poisson process. It's the
limiting
stress at which an event is certain. And because this is, we'll get to how events are decided to happen, but an event will happen mathematically before you reach X critical, but it can approach X critical.
Okay.
And time is in units of tau, and tau is a time scale where that's the time taken to accumulate X critical amount of stress in the absence of any stress events. And so tau will depend on how fast you're dumping energy into the system or how fast stress it's building up.
Right. Okay. Okay.
And I say here at the, just above equation 1 that it's doubly stochastic. Doubly stochastic here means that there's two things that are stochastic in this equation, and they're, not especially obvious. Well, one might be slightly obvious, but the first one, this delta xi, this is a random number.
Okay. So
the amount of stress that we say is released at each event is a random number drawn from a PDF. This PDF eta is kind of important. It's like a key control parameter of the model.
Yes.
User specified. You can decide what this is. A sort of canonical choice is the power law, because as astronomers, we love power laws.
Of course.
And we might be thinking, okay, how much stress is released at each time that stress is released? You might think smaller amounts of stress are released more from the big amounts. And there's going to be some connection between this stress release PDF and the observed event size PDF, but they're not the same thing. They're definitely not the same thing. One thing, this eta is conditional on the stress just prior to each event. So this conditionality is actually really important.
Yes.
So it's not just a fixed size PDF. It's conditional because we can't release more stress than there is in the system.
Yes. I'll agree with that.
And
you can empty the gas tank, and that's that.
yeah, you can't empty it out into negative stress or negative energies. We're not going there.
Not doing rubber bands, no.
So it's important to have this conditionality, and the annoying thing is that having this conditional bit in it actually makes this analytically difficult to solve. Now your equation of motion is basically this iterated thing where you have to actually track it over time.
Yeah.
Solving for a long-term thing, even like a long-term averaged thing, is possible for certain choices of eta, but certainly not all. Okay, so that's the first random thing. The first stochastic thing in equation 1 is delta x's. The second stochastic bit is n of t. These are when events are triggered.
Right.
So this is like a counting function where n will be 1 after the first event is triggered, 2, blah, blah, blah. So how do we know when events are triggered? Well, this is where it's a state-dependent Poisson bit. And so if we scroll down to the next paragraph. So here we're saying, okay, a Poisson process, a standard homogeneous Poisson process, has a constant rate. Lambda, the rate, is just not a function of time or space or anything else. It's just, it is what it is. However, in the state-dependent Poisson case, our rate, instantaneous rate,
Yes.
is a function of the stress currently in the system. And so this rate is constantly varying. And remember, this x of t actually is a doubly stochastic variable. And so this x of t is varying in a stochastic way, deterministic between events, but jumps after the event. And so your rate is also doing, is mapping to your stress.
Correct. Yep, I'm with you.
Now we have this sort of alpha on 1 minus x. Alpha is a control parameter.
Okay.
It's the dial that we're mostly turning. It's quite important. It's the way we sort of can tune the state-dependent Poisson process to get to different regimes of stress release.
Okay.
We'll see in the first figure actually what it actually does.
Okay.
Example what it does. But this sort of 1 on 1 minus x functional form for the rate is a choice. It's a choice that we have to make. We can make different choices. We did a bunch of tests, and we found that it doesn't actually change much of the results. For the state of the process, as long as we diverge as x approaches the critical stress.
Right.
The functional form of this doesn't particularly matter. The idea here is that your rate, this is encompassing that idea that we had earlier, that the more stress in the system, the more likely an event. Right? Yes. So as x approaches 1 or x critical, then our rate becomes larger and larger.
Yes.
On more likely events. And so this is encompassing that idea. Okay, so then, that's our rate. And then we look in some stats textbooks from the 1950s, and we work out that if we've got a rate that's non-constant, we can find what the waiting time is between events for a Poisson process with a non-homogeneous rate.
Okay. Yes.
That's equation 3 here.
Lovely.
Here, we're relying on the fact that our stress actually builds up deterministically between events. And a waiting time is, by definition, between events.
Right.
So we can just use this equation, which doesn't know that x is going to be doing jumps. It doesn't need to know, because all it does is start when we just had an event, work out probabilistically when is our next event going to happen.
Yep.
That's it.
Yep.
You can actually plug in equation 2 into equation 3, do the
pull the crank,
do a bunch of maths and work out what your PDF is. I don't actually write it down in this paper, but it's in other papers.
Well imagine doing it. There's your lambdas.
Yeah.
And go.
Exercise for the reader.
Yep.
Or listener. Okay, so then the point is, we've got the pieces, and I've explained why it might be hard to analytically solve this.
Yes.
Instead, we do a Monte Carlo automaton. Just iteratively pick waiting times and stress release sizes.
Okay.
And in this way, we can generate sequences of waiting times and sizes from the model.
Yes. So alpha.
And those sequences are going to be comparable. We can derive long-term statistics from these sequences, and we can compare those statistics to statistics from observations.
Okay. Be they Pulsar.
Especially if we decide to do these statistics in a way that doesn't, depend on the actual dimensions, right? In our model here, we're d-dimensional. We're got dimensionless units, and so we want to pick statistics that don't depend on the sizes.
Okay.
The absolute sizes of these numbers. But that's fine, we can do that. Okay, so I've already explained I've sort of outlined a little bit how how this maps to solar flares as we've been going along. One thing to sort of point out is that I sort of elided the fact that x here is a stress, but what is being stressed? you know, there's still some question marks here of like, what exactly are we modeling?
Right.
What we're doing is saying that there is some globally averaged quantity in an active region. So an active region is a sort of hotspot on the sun where most flares happen. And the idea here is that there's some energy reservoir associated with this active region, and this active region can sort of communicate with itself on such timescales that the stress is going to be averaged out.
Okay.
Now, I'm doing some scare quotes here because the spatial correlations and the exact sort of geometry of these things are likely to be very important. And we'll return to this, you know, at the end when we discuss, you know, what can we conclude from this.
Okay.
But for now, X is some globally averaged stress.
Okay.
So in 2.3, we say that, you know, it could be the globally average magnetic energy density. It could be magnetic shear, could be some other quantity that we want to decide on, something about the morphology or something else. But just assume you've picked something.
Okay, something to correlate with. All right.
Yeah. And the main reason we're a bit sort of loose here or flexible here is that, again, we're not actually tracking the stress itself. So we're not going to try and use data to track stress as a function of time.
Right. Because
all we need from our data is the sizes of the events and the waiting times between events.
Right.
And we can do this mapping between the mathematical process and the physical process.
Yes. Whatever that physical process may be.
Yeah, exactly. And hopefully, learning about what mappings work and what mappings don't work, it tells us something about that physical process.
Yes. Yes.
We'll find out that, of course, we're finding out what the physical process can't be rather than what it is.
That's just as valuable a lot of times, right? It's not this.
Okay, so in 2.3, the second paragraph, we lay out that there are some pretty other simplifying assumptions, not just that the stress is spatially average, but that this time scale of energy being deposited or stress being deposited, technically, that's also constant in time. So this is tau is constant in time, or tau inverse is constant in time.
Okay, fair enough. Yeah.
Which, I mean, over the lifetime of an active region might be okay. It might vary by maybe an order of magnitude. Okay, maybe that'll matter, but actually, I'll claim that it probably won't matter that much, mostly because, yeah, we'll get to it.
We'll get there.
And the other one is that this threshold, this critical stress, is also constant in time.
Okay, yeah.
And you might think, okay, well, if this stress threshold is something to do with the microphysics of like shearing, maximum shear, or some energy density at which some
reconnection happens,
starts turning on.
Right.
You could think of that maybe could be reasonable. But again, you could also think of reasons why it might vary. If it's not magnetic energy density, but magnetic energy that's varying, and then the shape is varying, then okay, maybe this threshold will vary. If we've got the wrong, mapping.
But let's start simple, constant.
Exactly. Okay, and so I've already explained that the STP process generates sequences of dimensionless waiting times and sizes, and then they're going to correspond to observable waiting times and sizes.
Yes, we hope.
Okay, and so that's what equations 4 and 5 are sort of saying.
4, yes, okay, got you on that one. And 5, yes, sure, okay.
Delta S here is the observed sizes, and delta X are the stress release events.
Yes. Okay.
Okay. So we'll get to figure 1 in a second.
Okay.
But just to sort of waylay the interested reader to be like, I know, we can make this an inference problem, right? We've got a bunch of unknown parameters, x criticals and alphas and lambdas and whatevers. We've got a bunch of observations. We've got a model. Let's just do the inference.
Right.
Turn the handle, Bayesian inference. It'll work. Get some posteriors out, and it'll be nice.
And
Um,
you'll have your corner.
so,
We're good.
yeah, we'll be able to show some corner plots and work, publish the paper. No, actually, this wasn't the first thing Andrew tried, and it turns out for good reason. He tried later with a different student of his, Lisa Drummond, in this paper in 2019, and it's hard for kind of technical reasons. Mainly that the likelihood is ill-behaved because it's this stochastic process with jumps. Your likelihood is very spiky. Both spiky and recursive because each stress release event requires you to know the full history of stress release events. And so for anyone who knows about sort of modern samplers, these are two things that are not very good.
They're not built for that.
A very complicated recursive likelihood that's also not concave or not convex.
Right.
A sampler struggles. So they did a bunch of good work here with like particle swarm filters and various other methods, but it's and this is an avenue for future work.
Yay, we'll come back to that. Okay.
We'll come back to it. Okay, so let's go to section 3, where we go to describe some sort of heuristic signatures of the state process.
Yep, alpha much greater than 1, alpha much less than 1. Okay.
So there are two broad regimes. There's sort of greater than 1 regime, which is sort of what I'll claim the boring regime. Not boring. It's the one that it's sort of much more flexible in what it can predict, which means that it's much harder to falsify.
Okay, yes.
And then there's the interesting regime where alpha is small. And when alpha is small, we have the stress building up close to threshold before every event.
Bang.
So if we go up to figure 1.
Right. I'm with you. Oh, yeah. This is good. Okay.
This is the two main regimes. And so start on the left with alpha much, much greater than 1. And 10 is much, much greater than 1.
Yep.
And you can see here that the stress is doing this thing of building up between events and releasing.
Yes.
But it's not really interacting with the top boundary, right? It's not getting close to threshold. In a lot of ways, it sort of doesn't know about threshold. Events are being triggered well before it gets close to the threshold.
Oh, yeah. Okay.
Which is fine and great, but again, not super interesting. The things on the bottom are waiting time and size distributions on log linear and log plots respectively.
Okay.
So you can see the waiting times here on a log linear, that's exponential. So we've got exponential waiting times. It's basically a standard Poisson waiting times.
Yep.
And then on the right, we've got the sort of weird size distribution shape. This is sort of determined by eta. Choose a different eta, you'll get a different thing. They're not one-to-one mapping again, but they'll correspond in some way.
Yes. Okay.
And this is, power law above a certain value. And
power law on the other side of the value. There we go.
Yeah. And that's sort of determined by, we chose here for our eta. You can see in the caption that eta is this power law with a lower cutoff to make sure it's integrable. Say that at least 1% of the stress of the system is released at each event.
Yeah. Okay. Oh, it's a heavy side. Okay.
Yeah.
Okay.
So that's sort of the uninteresting side. You can imagine here that there's not going to be many correlations between your waiting time and sizes because you're not going to be hitting the bottom of your reservoir and you're not hitting the top. And so these sort of the waiting times and sizes don't really talk to each other. They're not going to be interacting in an interesting way. On the other side, alpha equals 0.1, we can see our stress building up to the threshold much more quickly. It hits the threshold or gets very close to the threshold before an event is triggered.
Bang, 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 bang.
Yep. And so this is actually quite interesting, and matches a lot of what people sort of think about what's really behind the process.
Okay.
This is what people say in their introductions often. It's like stress will build up or energy will build up until a threshold is reached, and then it'll release some. And this is what we're saying. Stress will build up until a threshold is reached, basically, at this regime. And we have very precise predictions about what we should see.
Long term.
We should see okay, we don't have exponential waiting times anymore. We have power law waiting times.
Oh, okay. Uh-huh.
And we have power law sizes.
Uh-huh. DVDs.
And they're correlated.
Yep.
You have a big stress release event, you're gonna have to wait a longer time before you build up that stress again until you hit the threshold.
Okay.
So you'll have this forward cross correlation, forward waiting size to the forward waiting time.
Okay. Okay.
And so that's a clear prediction. And so these are linked as well, right? We'll have a cross correlation and we'll have matching waiting time and size distributions.
Correct. Okay.
And so this is a heuristic test, doesn't depend on the sizes of events, the real units or anything like that. These correlations are Spearman cross correlations, so they don't depend on the absolute size of the variates. And we can compare this data and see if we see the signature
in
cross correlation and matching size and waiting distributions.
Very cool. Okay, I'm with you.
Okay, so I'm just cognizant of the time a little bit. Let's go to figure 2.
Figure 2, and here we have forward and backward.
Yeah. Do we have a hard out, by the way? Should I be sort of aiming for a?
I think
you'll hurry me along.
I don't think we want to be here 2 more hours,
yeah.
but in an hour is good. If we're within an hour, good.
So this is actually like one of the key ideas is that the state-dependent Poisson, as I said before, doesn't just have 2 regimes, as we had in the literature earlier. It's a continuum. You can tune alpha. This is obviating the sort of complexity that eta brings into it, this other control parameter we have. But just thinking about alpha for the second, we can turn this knob and go between this uninteresting high alpha regime where we don't get any real cross correlations, and the interesting threshold driven regime. And so we can see perhaps where we are on this curve by looking at this cross correlations.
Cool.
And I have here the rho minus. This is the backward cross correlation.
Okay.
So this is when you have the waiting time correlated with the next size. So if you have a long waiting time, does that mean your next size is also big? And this might be the case if you're releasing your whole stress reservoir at each event. If you bottom out, if you empty out your tank.
Yes.
Which would require a particular choice of eta in the mathematical modeling, but you can do it.
Okay.
You can create the system, the mathematical system that does that. Okay, so and I've already described that. So let's go into section 4, actually.
Okay. GOES observations.
Yeah. So GOES is the geostationary operational environmental satellites. There's an S there because apparently there's been many of them. Apparently up to like 17, 18.
Something like that, yeah.
So these have been, operating for 50 years nearly. Looking at the sun and soft X-ray wavelengths, checking for flares and recording databases for flare summaries, which is what we used as our sort of data input.
Okay.
So in 4.1, I'm just sort of laying out, what timescales we're looking at. We basically just took the whole data set.
Yeah, I was going to say. Okay.
Getting some terminology down, waiting times, sizes, etc., etc. I don't think this is sort of important to the story I'm trying to tell here. But these are important details for people looking to reproduce it.
Always a good thing to do in a paper. Put some stuff and reproduce. Very good. Okay.
Figure 3, just some summary stats of for each active region. This is just looking at active regions with more than 5 events.
Yeah. Okay.
Because we need a bunch of events to be able to get these sort of long-term statistics. So just looking at those sort of active regions with many events, there's still a lot of them, tens of thousands of these active regions. Sorry. 2,500 active regions with more than 5 events.
Good. Okay.
And there's this distribution of, sizes NK is the number of events in a given active region. And then lambda k is the rate, the observed rate of flaring in each region.
With the units back in.
Yeah. So this is
Inverse.
not the lambda in equation 2 or whatever it was.
Right.
This is sort of a little bit tricky in that, they're subtly different things. One is an observed quantity and one is a sort of model internal parameter.
Reader beware.
Anyway, so there's 2,500 active regions that we're going to be looking at. There's going to be 40,000 flares in these regions. So that's great.
That's a bit of data. More than pulsars.
More than pulsars, where we have 5 or 6 pulsars with 15 events each. So it's a bit different. Different things we could do. But one thing to keep in mind is that with more data, we actually know some of our biases. And with we can study these in a bit more detail. So in 4.2, we go over some of these biases that probably exist in this database. And this is something that Mike, and others obviously know about and have known about for many years. Basically, the way that flares are detected,
right,
sort of depends on the past history a little bit. And so there's going to be this influence of, if you have a big flare, it's going to wash out a small flare that happens after it.
Yes. Yeah.
Which is a slight problem. Perhaps if we're going to be, trying to map these sort of time series of waiting times and sizes, we want to be catching both the small and the big events.
Right. Correct. Yes. Otherwise, you just dominated by the big ones.
Yeah. So this obscuration effect is important, and the how it will change our statistics is kind of perhaps a little bit subtle and hard to model directly, but we can do some sort of like broad, estimates by saying, okay, if you look under, equation 6, there's this sort of estimate that, okay, well, how much is our peak flux going to be influenced by the sort of decay of the previous flare? And we, look in the catalog and see that, perhaps only 1% of flares might be affected by this.
Okay. Got it. Okay. Right.
Which,
right. Okay.
Hopefully we're sort of safe, but we should keep in mind when we're, interpreting our results that there is likely this effect of big flares washing out subsequent smaller flares. That happens soon after. Okay. And of course, there's the classic thing of we can more easily see big events than small events, right? Yeah. So our completeness at the sort of small end is going to be suspect.
Yes.
This is just true, everywhere.
Yes. Generally true. Small ones get washed. Okay.
4.3, we just do some aggregate statistics, some more aggregates, where we say, okay, let's just ignore the fact that we've got active regions, really, and just lump everything together. Okay. What's our waiting time distributions and our size distribution for like the whole database data set?
All right, that sounds interesting.
Just to sort of get an idea of what our data looks like, sort of on the whole. And so you can see in the top panel, the waiting times are actually sort of most well fit with a log normal, which is sort of, slightly unusual for a sort of random event. Yeah. They're certainly not exponential, and they're certainly not a power law.
Definitely not. And definitely not. Okay.
So it's sort of interesting, and we have a little appendix that discusses this. And you can refer interested readers to that appendix if you want to know more.
There's 5 killer appendices. Check them out.
Yeah. But again, this is an aggregate, and so this is summing over many different active regions, and this has been noted before by other authors. And when you look at individual active regions, which is what we'll do next, we see different things. Okay. And it might be the fact that we're sort of superposing many different PDFs on top of one another that constructs this log normal. It's not actually inherent to the process.
That's an interesting idea. Okay.
Our sizes here, the size distribution on the bottom, what's in gray is what we are sort of suspect of, right? This is from the obscuration effect, where we're not confident that we've seen events smaller than this 10 to the negative 3 number.
Joule per meter squared.
Okay. The units here are peak flux multiplied by the duration of the flare. That's the size.
Right.
So this is sort of like a proxy for total energy release or total energy density release.
Yes. Yes. Okay. Where's our log normal?
Yeah, so here you're like, okay, well, the power law sort of fits best, especially if you ignore the stuff below 10 to the negative 3.
Right.
But again, it's not super clear cut. But again, we're superposing many different PDFs on top of one another, basically.
Right. Okay.
So let's not do that.
Right.
Let's look at individual active regions.
There
This
we
was
go.
the whole idea, right? Each active region will have its own sort of reservoir, and these different active regions won't be communicating with each other. They're,
Yep.
perhaps decades apart in time or in space,
Right.
different sides of the sun. So there's no reason for them to really be thinking of each other's stress in any way. Okay, so actually one way to sort of look at this is to go to Appendix E.
Let's go to Appendix E.
So it's page 13. So if we just pick out a few active regions, we're going to pick some active regions with more than 20 events, just because that way we can plot some PDFs that look somewhat nice.
Yes.
We can, scroll down and see these various fits of which shape best fits for various regions. So on the top left, we've got this very early AR2645 region. It's got 25 events in it. And I've got a log normal waiting time distribution, or best fit with a log normal, but you could also convince yourself that's an exponential.
Yeah. Okay.
And the waiting times are probably a power, the sizes are probably a power normal, a power law. So that's the just below it, and yeah.
Oh, gotcha. Okay, I was going.
Yeah, sorry, it's sort of like a stacked quadrants.
Okay. Yeah. No, it's good. I'm with you.
That's okay. We've got a log normal and a power law. We've got on the right a power law waiting time and a power law size.
Yeah, power law.
So here we're determining best fit using a sort of the Akaike information criteria.
Okay.
Just basically comparing the maximum a posteriori likelihoods. There's some assumptions there about statistics, but sort of not super relevant to this work. And then in the bottom, we can see, this 11967 has got log normal and log normal.
Yes.
And then on the right, we've got exponential and log normal. So it's like this, what we're showing here is that there's a variety of different shapes and sizes for waiting times and size distributions.
For individual regions.
And we can do this sort of fitting. Like, sure, with 20 events, your statistics are, broad, but you can do this comparison, right? Which shape best fits it, compensating for the number of parameters in each of these classes. It's very doable, and you can sort of quantify which ones are best fit. And that leads us back for the scrolling back to figure 5.
Okay, let's go to figure 5, the FL plot.
Yeah. Oh, and there's an FL below the figure as well.
Got FLs below.
Yeah, so the reader shouldn't read anything into the FLs. So in the top panel here, we've taken every active region with 10 greater than 5, done this sort of estimation of which shape best fits.
Okay.
Of the 3 options we had, and then binned them according to their rate. So basically their inverse average waiting time.
Yes.
Just to see whether there was any trend.
Okay. All right.
And so we were like, okay, we see lots of exponentials for low rates. We see, some log normals. We see some power laws. We should remember that each of these rate bins is not equal. There are different numbers of events in each of these bins, and that's what the black line is showing. It's a CDF of active regions. Active regions with rate less than that value.
It's cumulative. Uh-huh.
So you can see most active regions are in that sort of, bins 3 to 6 in lambda k. And so those have the most information. And so the variance on these sort of things is, we should be thinking about these bar plots, stacked bar plots, so having some fuzzy edges.
But yeah, sure. Okay.
But we can still try and look for trends, right?
Oh, yeah.
And we're sort of seeing perhaps that there's fewer exponentials as lambda increases.
Yes. Green area.
Right. Going from 0 to 0.1, we go from, 75% being exponential to maybe 50%.
Okay.
So that's that blue.
Yeah, it's blue. Yep.
And it's like, okay, well, can that make sense for state-dependent Poisson? If lambda k is some tracer of something in the state-dependent Poisson, what is it? What's the tracer? We've plotted this, we've binned it in terms of lambda k as sort of, we're inferring something here. We're saying something. We're saying,
yeah,
actually, perhaps lambda k is related to alpha.
Ooh.
So why? You might ask.
Why?
You can do a bunch of maths and perhaps empirical simulations if you wanted to, and work out that the average waiting time goes as 1 on alpha plus some number of order unity.
Okay.
But that's d-dimensional waiting time.
Yes.
You do the inverse of it. That's your rate, right?
The
inverse of the average waiting time is your rate. And so your rate should go as alpha plus some number. Proportional to.
Interesting. Okay. That's nice. Very cool.
So we actually, as we said before, we actually should be seeing more exponentially standard Poisson stuff at big alpha. So big lambda. Which is not what we see.
Right.
So we're going slightly against perhaps what the state-dependent Poisson predicts.
Yeah.
Interesting, but not conclusive, that's for sure. The sizes are a little bit less sort of informative. They're mostly power laws, and there's not really much evolution happening there.
Right.
But the interesting thing here is that we do have multiple sort of shapes represented. It can't all be power laws. Not all active regions are best described with power laws, which is sort of interesting in its own right, because to get that in the state-dependent Poisson sort of case, if there's a state-dependent Poisson behind each of these active regions, we would need eta to change in each active region to explain this. Eta was the same across all active regions, then we shouldn't see such a variety of size distributions.
Okay.
So that's a little odd, right? There's this internal control parameter that has something to do with how much stress is being released at each event.
Right.
And why would that vary per active region? Okay, maybe it's a function of some morphology, maybe a function of geometry, of some energy inflow, there could be many reasons why, but there isn't just one simple answer of it's a power law.
Right.
Which is a bugbear of mine, that things can't just be power laws.
Not always.
Figure 6 is a sort of another looking at individual active regions. Here again, so in the top panel, this is just the data. We're just doing histograms of the forward cross correlation and backward cross correlation. The distribution for backward cross correlation peaks at 0. It's normally distributed. It's pretty typical distribution given the numbers of events that we're doing these on. If you've got 10 events, it's not unusual to get maximally correlated things, but your error bars are huge.
Right.
For the forward cross correlation, it's slightly skewed.
Right. Toward
to the right.
Right.
But this is easily explained and has been historically noted that the obscuration can generate this, right? If after a big event, we're obscuring the small event after, we're going to artificially slightly inflate our forward correlation.
Correct. Okay, I'm with you.
Completely, consistent with that bias.
Mm-hmm.
The bottom panel here is another one of these, does this make sense with state-dependent Poisson? Where again, lambda k, we can think of perhaps speculatively as a proxy for alpha.
Huh? Huh?
So if lambda k grows, alpha should be growing. And we actually, remember at the start, we said alpha low is high for cross-correlation.
Yes.
And so actually we should be looking for a downward trend in this plot, in this scatter plot. We don't see any trend really. You can, by eye draw various lines, but no, there's basically no trend. Perhaps if anything, slightly upwards, but
yeah,
again, almost certainly driven by the obscuration.
Yeah. Mm-hmm.
So there's no clear sign that we're seeing lots of these sort of high cross-correlation threshold-driven regions.
Correct. I'm with you. Yep. Mm-hmm.
Let's keep going. And I think 5.3 is sort of the money plots of the paper.
Which one?
Section 5.3, so figures 7 and 8.
There we go. The money shots. Oh, here we go. Actual real data. Okay. Let's do 7.
So these are actually sort of together in a lot of ways, but we can look at 7 first.
Okay.
And this is coming back to what we were saying at the start, is that there's this sort of heuristic test we can do with forward cross-correlation and this matching between the size and waiting time distributions.
Okay.
And this is a way to quantify that. And so we've done a bunch of simulations with the state-dependent Poisson process, turning alpha to different values. And so the top panel is forward cross-correlation on the y-axis, bottom panel is backward cross-correlation on the y-axis.
Yes.
On the x-axis, so we have this match, which is quantified with a Kolmogorov-Smirnov statistic.
Okay. Okay.
We just see whether these two distributions are similar to each other.
Okay.
Two distributions in waiting time and sizes. Oh. And so we want to find if we have small alpha in many regions, we'll find many points up in the top right corner of this plot. So this is that sort of dark orange. They're all concentrated up there. And these contour lines are denoting sort of 10, 50, and 90% sort of credible intervals.
Okay, I'm with you. Mm-hmm. Yeah.
They're sort of kernel density estimates over a scatter plot, basically.
Gotcha. Okay.
And so as you can see, as alpha increases, these sort of contours spread out. We're doing simulations using the number of events like we have in the real data. So this is sort of folding in the uncertainty we'll have due to that limited number of events.
Yeah.
And so you can see that, yes, we see this matching happening a lot of time, even with high alpha, but a lot of that is just due to noise.
Okay.
But it's this, correlated statistic of the cross-correlation and the match that we're looking for. And in the backward cross-correlation, we shouldn't really see anything. But the match contours still move based on alpha, right?
Yes, they do. Yeah, definitely they move.
Okay, so this is our prediction, right? We're now asking if we have the same alpha in each region, we should get one of these contour lines from the real data.
Populated region, yes.
And so then we move over to figure 8, and this is the real data. We're definitely not in the small alpha regime.
Yeah, right.
In every active region. Right. Perhaps there's some regions that have small alpha, but certainly not every.
Yeah, not by bulk.
Certainly not as a whole.
Right. This one.
Which is pretty interesting because now we're saying, okay, we're not in this threshold-driven regime.
We're not. Right.
Like the threshold isn't deciding when flares are triggered. We're not being driven there every time. Maybe for some flares, maybe for like the biggest ones, or for some active regions, but certainly not as a rule.
Okay, so this then must be saying something about the model, or
yeah. So now we're saying, okay, well, does this tell us what the physical process is? right? Does this say, oh, we've got the Lou Hamilton avalanches?
Okay.
No, not necessarily. Because again, we can be doing this stress relax thing, but just not stressing to a threshold.
Okay.
We
Sure.
still have stress relax happening. We're just not interacting with that top threshold.
Mhm.
That's still an adequate explanation, mathematically adequate.
Okay.
Physically, we might believe one or the other, or through other arguments and through other observations, we might believe the sand pile's better or something. But we definitely, can show here we're not hitting the threshold. This threshold isn't determining events.
Okay. All right.
Okay, so then the last little subsection before the conclusion was this idea of autocorrelations and longer term memory. So this stage, we only looked at sort of one step removed memory.
Right.
We looked at a waiting time and a size.
Right. What if there was 10 or 100 or?
Yeah. So you could actually look at like waiting time and the next waiting time, or many removed, whether there is a long-term memory of the stress in the system.
Okay.
If your stress is building up a huge amount, but then releases sort of slowly through many subsequent events, there's still a memory of that high stress.
Yes.
Which might, turn up in the long-term statistics of these events,
Mm-hmm.
which isn't captured in a sort of avalanche model, which explicitly says there's nothing, right? There's no, we're not having cross correlations because we're saying that each event is sort of independent and the system is big enough and distributed enough.
Right.
It's critical in that way. And so we sort of, we just do look at that one step removed, waiting times and waiting times. We don't see anything. But this is sort of kind of to be expected for the state-dependent Poisson process. It doesn't actually predict much long-term memory, except in very sort of like, you turn the handles a very precise way, you can generate it, right? You have a very particular choice of eta or a very particular choice of something or other. You can see some of it. So we can rule out those very weird regions of the state-dependent Poisson process because we don't see these sort of long-term autocorrelations.
Right. Which was there. Right. Right. It is the money shot.
So,
okay.
What do we conclude?
Yes.
Well, in a lot of ways, this paper is sort of bringing a machinery back to the solar flares context. Mike and many others have developed this. A paper from Mike in 2008 was, really, inspirational for Andrew to go to the Pulsar glitches with it. But this, we've sort of developed it a bit further and worked out, okay, well, how can we make predictions and how can we falsify regions of this mathematical model?
Yes.
And how does that inform us about the physics of what the process is? Okay. So if we have a constant driving rate and a constant stress threshold, we know that solar flares are not in that regime where the stress reaches the threshold before each event.
Right. That was
so that's the main conclusion.
Okay.
Which is sort of interesting. A lot of people say that this is what should happen. But there are ways to interpret this, right? That are not just throw the baby out with the bathwater. Perhaps these assumptions are not true. Perhaps the threshold varies with time, the driving rate varies with time, and varies in time in a way that washes out these sort of heuristic tests that we're looking for. Which is eminently possible. The other possibility is that our data is incomplete in a way that also washes out these statistics. Maybe we're missing so many events that we're just not seeing the whole picture.
Right.
We hope that isn't the case, and we don't think it is. But as we saw with the sort of obscuration effects, we can get these artificial cross correlations, which we have to sort of be careful about interpreting.
Yep. Okay.
And okay, well, how do we, where do we go from here, right? There's this sort of question of, we have this broad model, and it's quite sort of all-encompassing, and we've excluded certain regions of it applying to all regions. There's different things we can, different places we can go, right? We can think about, okay, what other broad mathematical models could explain the sort of distributions of solar flare statistics that we see. We did a bunch of work in Pulsar Glitches that was along these lines of different sort of what we call meta models, where the state-dependent response was just one example. You can build stress in different ways, perhaps have your stress accumulate via like Brownian motion. The threshold is reached. And this is sort of, a lot of people in solid phase community might believe that more, right? The idea that you have this secular increase in energy, very straight line, very deterministic, feels a little off, right? Because what you really have is these sub-photospheric motions sort of pushing foot points of your, magnetic arcades around, and that might actually be literally Brownian motion, which might result in a Brownian stress accumulation.
Oh, yeah.
Perhaps.
Maybe.
So that might be a sort of mathematical model way we can sort of approach, making different falsifiable predictions. We might go the other way of saying, okay, well, let's try and get to the bottom of the data. We're using at the moment these sort of summary data, which is generated by these sort of automated algorithms that do a great job as a first pass. But typically, sort of the broad, like, flare studies are done on individual flares or individual active regions rather than all active regions at once. And so reanalyzing the sort of time series of flux to really try and pick out those small flares might be interesting, might be a sort of a way to sort of get to the bottom of, are we missing lots of small things? Are those small events important?
Pun intended there, right? To the bottom.
Yes. And there's a variety of other avenues we could take, but they're the main thrust that we're thinking about. I know Mike has recently hired a new postdoc who's starting in this field and is hopefully going to be taking over and doing the next work here. And the other avenue is, and the last thing I want to talk about is sort of going back to some stats in Appendix B.
Let's go to Appendix.
And, a sort of pulling back the curtain a little bit. Appendix B was where this project started for me, where we were trying to do this thing where actually inferring parameters. We were trying to sort of lay out this mathematical model and try and infer something like tau or X critical.
Okay.
Because you have maybe this feeling, or you can make the assumption that perhaps they don't vary too much region to region. And if they don't vary too much region to region, and you've got lots of different regions that are pulling from this overarching parameter, that's a hierarchical Bayesian model. And we can do some hierarchical inference to infer the population level parameters. Great, sounds great. But we run into the ugly problem that, yes, the likelihood is too bad.
Oh, rats.
Yeah, rats.
Rats.
And you can do this special case where you have a very particular choice of eta in B1.
Yeah. Okay.
Where it's this funky functional form. You get some more analytic results. You can make the likelihood actually a bit more well-behaved, but it turns out that the data doesn't look like this. When you look at the long-term stats for this sort of eta, it just doesn't match the data. And so we couldn't apply it to real data.
Okay.
But we could maybe think about doing some different funky things with, approaching our likelihood a different way, or approaching our inference a different way. In section B4, we sort of outline an approach to just use the average waiting time instead of using full likelihood, and use an approximation for the likelihood.
Right.
So various avenues, and in figure 9 we have this sort of the ideal world of, I've injected some fake data.
Okay, right.
I've recovered it using this hierarchical model. And these are the sort of population level parameters and a posterior predictive check. And so we can see that we've done pretty well using the fake data and our but again, couldn't apply it to real data with what we had. And so we decided to instead focus on this question of, okay, can we just rule out that we're in the threshold driven regime?
Yeah, right. Okay. Which is a good, fine
Yeah,
conclusion.
which is valuable in its own right. But
Yeah,
you know,
exactly. Very cool. Very cool. Julian.
okay, so I think that's all I wanted to say. But happy to.
Well, Julian, well, thank you so much for walking us through your very awesome article.
Thank you.
Very nice. And you touched on it a little bit there toward the end on sort of future directions on different ways to approach the modeling or the math. Is there something that could be done in the future as far as the number of data points? For example, is Parker, can Parker do anything for us? Can we ever envision instead of 40,000 points, we have 4 million points or something along those lines?
Yeah, so it's a good question. So there's two ways to answer it, right? There's at the moment the GOES data is the soft X-ray data, and this has a lot of value in that it's a historic data set of 50 years. It's complete in the sense that they've been looking for 50 years with a very consistent sort of methodology.
Yes.
It means that we have similar biases along the whole way. We could look at different wavelengths. Hard X-rays, for example, have less of this obscuration effect because the energy release sort of dies away much quicker in the hard X-rays. But the data sets there are less complete. So there's fewer data points actually there, but less obscuration. I don't know particularly about Parker, but the idea that we could try and use more data points is quite interesting. And this is something that Mike's new postdoc is thinking about, Nastran Farang. She's got some lovely data, I think actually in the hard X-rays of time series, sort of energy as a function of time during a flare.
Ooh, okay.
So this is sort of thinking about, okay, instead of thinking about a flare as an instantaneous event with a jump,
bang.
Can we learn something about how the energy evolves during it?
Yes.
There's some, Brownian looking things happening and maybe some small fluctuations of stress increasing and releasing during it. Can we model that smaller time scale, like zoom into a flare and think about that as a stress release system?
Okay. Okay.
Maybe. And that would give us much more data. Whether that's data that's sort of like, I don't know, as valuable as each waiting time and size, maybe not, but it's certainly a different sort of inference, right? You're doing a full-time series inference where you have to have a model that is a continuous model rather than this point process model.
Yeah. Cool.
But definitely a possibility.
Okay, cool. Well, I really look forward to seeing this field evolve over the next couple of years. Very interesting to get a handle on the processes of these solar flares. So very cool. Very cool. Julian, thank you so much once again.
Thank you.
And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.